Greetings, everyone. Hope you're having a great day. My name's Ryan Jackson, and today we're going to be talking about motor circuit conductors and overcurrent protection. And we're going to do this kind of on an intro basis. I don't want to get too deep in the woods on really abstract motors, DC motors and synchronous motors and thermal protectors, things like that. I'm going to keep this somewhat basic, but still useful. So let's go ahead and get started, and we're going to start somewhere that you might kind of find unusual, and that is with my main man, Sir Isaac Newton. He wrote this little book back about 350 years ago called Principia Mathematica, which is the principles of mathematics. And in that book, he introduced the world to calculus and his three laws of motion and Newtonian physics, his theory of gravity. A lot of people consider it to be like the most important scientific work ever produced. And one of the things that he says in the Principia is in Newton's first law of motion, it tells us that an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an outside force. And of course, that's paraphrased, right? For those of you propeller heads out there, like, that's not what it says. It's pretty close to what it says. So Newton's first law says things that are not moving, they tend to stay not moving. And things that are moving, they tend to stay moving, right? Now, what does that have to do with us? Well, it has to do with us quite a lot when we talk about motors. A motor that is not running does not want to run, because if you think about a motor, they are moving, right? They're turning. So a motor that is not turning does not want to turn. That's what Newton's first law, inertia, would tell us. Additionally, a motor that is turning wants to continue turning. All right. So what does this ultimately say when it comes to electric motors? Well, what it means is starting a motor is significantly harder than keeping it running. All right. If you ever pushed a car that's stuck or that ran out of gas, right, or something that's stalled, once you get the car rolling, it doesn't take that much to keep it rolling. But when it's stopped and you have to get it started, that's the hard part, right? Because when the car is stopped, it wants to stay stopped. When the car is moving, it wants to stay moving. So same concept here. When you're starting a motor, it takes a lot more energy than keeping the motor running. So when we start the motor, it takes a massive amount of current. And we can call that inrush, we can call that starting current, but it's all the same thing, right? So it's getting that motor moving. I have a bandsaw in my garage that I often use as an example. And my bandsaw, you push the start button, and when the motor kicks on, the lights in the garage dim, right? And the motor groans and it starts going. And the bandsaw, moves a pulley, right, which has another pulley and the saw blade attached to it. And once the blade starts moving, I can push the off button, and I actually have to stand there for the sake of safety. I actually have to stand there and wait for the thing to stop moving. And it takes like 30 seconds or so for the saw blade to stop, because again, getting it started is what's hard. Keeping it moving is the easy part. And this is really going to tie in when we start looking at motors, how you size the wires, how you size the breakers and fuses. All right, so just kind of keep that in mind, and then we're going to jump in to the NEC. So starting with section 430.6. If you don't read 430.6, you have absolutely no chance of getting anything right in Article 430. Absolutely no chance at all. You have to read 430.6 because it tells us the principles on how we size conductors and how we size overcurrent protection. So let's go ahead and jump in to 430.6. 430.6A1, and again, we're not going to cover all of Article 430. We're just going to cover some basic fundamentals here. The full load current values, the FLC values in tables 430.248 through 430.250 are used for conductor size, the rating of switches, and the short circuit and ground fault protection devices for motors and motor circuits. So we use the NEC tables, not the nameplate current, okay? So if I were to move my little table here on the graphic and move it off to the side, you would see that this motor has not only a voltage and a horsepower, but it also tells us the current. Well, what we just read is we don't read the nameplate when it comes to using motors for conductors, the ratings of the disconnecting means, and the short circuit and ground fault protection devices. We don't use the nameplate, we use the NEC tables, all right? So here's the motor. It's 115 volts, 1.5 horsepower. So I'm going to look here at my table, and it says, okay, I've got 1.5 horsepower motor. At 115 volts, that means it pulls 20 amps. At 230 volts, that means it pulls 10 amps. Now, in reality, this particular motor might pull slightly more or slightly less current than those table values. But here's the thing. We're going to size the conductors and the breaker/fuse and the rating of the disconnect not on the nameplate values but the table values. And here's why. All motors are slightly different, okay? If I have a 1.5 horsepower from manufacturer A and a 1.5 horsepower from manufacturer B, they're going to have different efficiencies. They're going to have little tiny differences. And one of them might pull 10 amps. The other one might pull 10.8. Another one might pull 9.1. So imagine if that motor burns out, okay? If that motor dies and I have to replace it, I'm going to go to Motors R Us and I'm going to say, hey, I need a 1.5 horsepower motor. I'm not going to say I need a motor that pulls 9.1 amps or 10.8 amps. I'm going to say I need a 1.5 horsepower motor. Which motor are they going to give me? Are they going to give me one that pulls 9.1 or 10.8? Well, that could change everything, right? If we sized the wires and the disconnect and the breaker or fuse, if we sized it on the nameplate, then every time I changed out the motor, I'd have to rewire the building, right? I might have to pull in new wires and change out the breaker, change the rating of the disconnect, right? And obviously that's going to be a lot more work than we want. So what the NEC says is it says, listen, we're going to pretend that for the conductors, the rating of the disconnect, and the ground fault and short circuit device, we're going to pretend that all 1.5 horsepower motors are created equal. And we're going to say if it's a single phase motor at 1.5 horsepower, 115 volts, it pulls 20 amps. And at 230 volts, it pulls 10 amps. Even if it's slightly more or slightly less, these are the horseshoes and hand grenades numbers that we're going to assign when it comes to these three things: conductors, rating of the disconnect, rating of the ground fault or short circuit protection device. Now there is an exception here, 3 exceptions, but I'm going to talk about exception 3. It says motor operated appliances that are marked with their horsepower and their full load current must have their conductors, controllers, ground fault, short circuit protection, and overload protection based on the nameplate current. All right, so next time you look at a motor operated appliance like a garbage disposal, like the one we're looking at here, there's kind of an unwritten rule, an agreement, a gentleman's agreement, if you will, between the manufacturers that kind of says, you know what, we're going to just call this motor a 3/4 horse, even though it's not. We're just going to say it's a 3/4 horse motor. And then, of course, people go to Lowe's or Depot and they're like, oh, look at that, 3/4 horsepower. And then that's what they get. The reality of it is it's probably not a 3/4 horse. So what this says is for appliances, we recognize that the manufacturer might kind of exaggerate the power of their motor. So for motor-operated appliances that have both their horsepower and their full load current, then we're going to use the nameplate full load current. Okay, so for this motor, I'm going to say 9.5 amps. For this motor, I'm going to go to the table and I'm going to say at 120 volts, it's 20 amps. 240 volts, it's 10 amps. All right, so when do you use the nameplate? When do you use the NEC tables? Critical that you understand that, okay? So generally speaking, we use the tables. Table 430.248 for single phase, 430.250 for 3-phase. We use that table for sizing the wire, sizing the disconnect, sizing the ground fault and short circuit protection. If we have a motor operated appliance with a nameplate that says the FLC and the horsepower, we use the nameplate FLC. Lastly, the motor's nameplate current rating, the FLA, not the NEC's full load current value, is used for sizing separate overload protection. All right, once we start getting into big motors, we usually have to have what's called separate overload protection, okay? We're gonna have ground fault protection over here, ground fault short circuit protection over here, overload protection over here. We're gonna size the ground fault and short circuit protection using the NEC tables. We're gonna size the overload protection using the nameplate of the motor, because when it comes to overload, overload is motor specific. And if we have a 9.1 amp motor and a 10.8 amp motor, those are going to be sized differently when it comes to overload, because overload is a lot more precise. Ground fault and short circuit is a lot more kind of, 200%, 250%, whatever. When it comes to overload protection, it's sized precisely. So for the nameplate, we're going to use the actual motor's information, the current. For conductors, rating of the breaker, rating of the disconnect, we're going to use the NEC tables 430.248, 430.250. So when it comes to sizing overload protection for this motor, pulls 14 amps, we're going to size that at 14 times 115%, which we'll talk about later on when we get into overload sizing. All right, so the motor's nameplate current, not the NEC table's FLC value, is also used for motors that are bigger than those in the NEC tables. So when you're putting your eyes on 430.250 and you're looking for three-phase motors, you're going to see that eventually the table stops, right? And it stops long before we reach 2050. That's a big motor. So how do you size a 2,000 horsepower motor? Well, for that, once we get past the NEC values, you actually do use the nameplate, because we have no other way to do it. All right. So for big motors, go ahead and use the nameplate. All right. What does this have to do with us? Well, when a motor starts, it's in what we call locked rotor condition. And the motor's locked rotor current is much greater than its running current, also known as the full load current. Okay, so starting current is the locked rotor current. Running current is the full load current. Let me just kind of show you a quick example here. This is a fire pump motor. And if you're following along in the code, 430.7b is where I'm at, locked rotor indicating letters. It says code letters on a motor are going to be used to determine the motor's locked rotor current. Now, just kind of take a breath for a second here. Not too often do we have to actually establish the locked rotor current. Okay, usually you just use the NEC table values, and then you use the nameplate, and you size the ground fault short circuit, you size the overload, and away you go. But there are some instances, like for fire pumps, where you have to establish the locked rotor current. And this section tells you how to do it. It says you use the code letter on the motor. This one is code J. But the reason I'm showing this isn't to teach you how to do this necessarily, although I've got an example here, and you push pause and you can do the math and figure out how to do it if you want to learn that. But the reason I wanted to show this is if we look at the running load current, the full load current, it's 4 amps. Okay, this motor pulls 4 amps. But if I do the math and I look at the locked rotor current, the locked rotor current is actually 30 amps. So a lot of people will tell you that the locked rotor current is about 6 times the starting current of the motor. And I don't want to say that that's inaccurate. It's sometimes accurate, right? But nobody is saying it's exactly 6 times. People say it's about 6 times, and sometimes that's true and sometimes it's not. In this case, locked rotor current was actually a lot more than 6 times. It was about 7.5 times. So all that I'm trying to point out is this. When this motor is running, it pulls 4 amps. When it's starting, it pulls 30 amps, all right? So if you put this on a 5 amp fuse, and that's all you had, right? You came right from the utility, and you bought a little 5 amp fuse, and you tried to start this motor, what do you think would happen? It would never start. It would burn the fuse, and the motor wouldn't start, and there you go, right? So we have to treat the motor starting differently than the motor running, okay? Let's get into some of the rules. 430.22. The conductors for the power circuit of a motor are sized to handle the running current, not the starting current. All right, so if we go back to that example we just did, 4 amps to run the motor, 30 amps to start the motor. Well, how do I size the wire? Do I have to size it for 30 amps or for 4? The answer is for 4, because yes, that thing pulls 30 amps under starting. But how long does it actually take to start the motor? The answer is not very long. Not enough that we're going to melt the wire. Okay, so for that motor that we just looked at, we could run that with 14 gauge wire, all right? And we could probably put it on a, without getting too carried away here, let's just say 30 amps, okay, for that motor. So 14 gauge wire and a 30 amp breaker. Well, most people are freaking out, saying, wait a minute, a 30 amp breaker doesn't protect a 14 amp wire. Well, but hang on here. How long is that 14 gauge wire going to be subjected to the 30 amps? About that long. And then the rest of the day, it's going to see 4 amps. So you're not going to damage that wire during startup, okay? The startup current isn't that much higher. If the startup current was 100,000 amps, well, then maybe we'd be worried about it, right? But it's not. So we're going to size the wire based on the full load current, based on the running current, not the starting current. The breaker or the fuse is rated to handle the starting current, not the running current, all right? So the breaker has to allow the motor to start while still protecting the motor. So we're going to size that to handle the starting. We're going to size the wire to handle the running. So conductors are sized based on the duration of the motor running. Okay, what I mean by that is, how long does the motor run? Does the motor run for 5 minutes, or for 5 hours, or for 5 weeks? Think of an escalator, for example, right? Think of an escalator at an airport. You ever been to the Atlanta airport? Busiest airport in the world, right? Escalators that have been on nonstop for God only knows how long, right? Not 3 hours, but 3 months without ever shutting off. You're going to size that a little bit differently than the conductors for a garage door opener that goes and then it goes, right? And it starts and it stops, whereas an escalator never stops. So we're going to size the wires based on the duration of the motor running. This part is critical, okay? Understand this. All motors are considered continuous duty unless they have a stopping point and a starting point, okay? So when we look at Article 100 and we go to continuous, right, a continuous load is a load that runs for 3 hours or more. This has nothing to do with motors, okay? The continuous load is not a motor thing. Continuous duty is a motor thing. Continuous duty means that it does not have a definite starting and stopping point. Let's look at some definitions here. Here's an escalator, right? A moving sidewalk, rather. Moving sidewalk at an airport. That thing is going to turn on and it's not going to turn off all day long, right? That thing might run for a month and a half before somebody shuts it off. That's a continuous duty. That means it's operating at a substantially constant load for an indefinite duration of time, okay? All motors are considered continuous duty unless they have a solid stopping point and starting point. Think of a disposer under your kitchen sink. You turn that thing on. If you walked away from it, it's going to keep on running, right? It's going to keep on running. But your garage door opener, you push the button and walk away from it, it's going to stop, right? It's going to stop at the top or it's going to stop at the bottom. That's not a continuous duty motor. We have intermittent duty motors. This means that it's operating at intervals of load and no load, or load and rest, or load, no load, rest. All right, so here we have a wheelchair platform lift. So if I'm in a wheelchair and I need to get up these stairs, I'm going to pull up to the bottom of the stairs here, right? And I'm going to push the button, and that chair lift is going to move down, which means it's under no load. Then I'm going to get on it, push up, and it's going to take me up under load, right? Now I'm on it, so now it's going to go up. So rest, load, no load. Passenger elevators, wheelchair lifts, things like that, those are intermittent duty. We also have periodic duty. which means operating intermittently with a load that's regularly recurrent. All right, so here I've got a conveyor, and this is at a power plant that's coal-fired. So they load this conveyor up full of coal, and they transport it for like, oh, I don't even know how far up, 1,000 yards, something like that. I mean, it's a substantial distance, right? So they load this thing full of coal, and then they move the coal into the area where it crushes the coal, and that's what the belt does, right? And then it stops. And then they might reload it a few hours later and then run it again. So it operates intermittently with a load that's regularly recurrent. Okay, that would be a periodic duty motor. We also have a short time duty, which means that it's operating at a substantially constant load for a short time that's definite and specified. A garage door opener, right? A garage door opener has the same load every time you push the button, the weight of the door, right? And it has a short time, and it's definite, and it's specified. The duration is whatever it takes to get the door from here to here, and it's the same load every time. That would be a short time duty application. The last type that we have is varying duty, and that would be a motor that operates at loads with wide variations and durations of time. Okay, so different loads, different durations of time, varying duty. So it's not quite as important to me that you memorize the different types, right? The varying duty and the short time duty and everything else. What's really important, remember that all motors are considered continuous unless they have a starting point and a stopping point. Okay, that's the part you really want to remember. So let's get into sizing the conductors. Conductors for a single continuous duty motor must have an ampacity of at least 125% of the motor's FLC as determined in the NEC tables. Okay, so I'm going to say it one more time. Actually, I'm probably going to say it 10 more times. How do we size conductors? Do we use the nameplate current or do we use the NEC tables? We use the NEC tables, all right? So looking at this motor, if I'm going to spin this thing at 115 volts and it's 1.5 horsepower, I'm going to go to table 430.248, single phase motors, 1.5 horse, 20 amps. So if we read the rule again, conductors have to have what? An ampacity of at least 125% of the motor's full load current. So I'm going to take 20 amps times 125%, and I would need what? A 25 amp wire. If I was running this at 230 volts, that would be a 10 amp load, and I would take 10 amps times 125%, which would be what? 12.5 amps. So I would need a 14 gauge wire, right? A 15 amp wire. Let's do this example here. 1.5 horse, 115, 230. Same exact criteria as the last motor. So I'm going to see if my math was right. If I'm running that at 115 volts, that would be a 20 amp load according to the NEC table. I'm going to size that at 125%, which means 25 amps, which means if I have 60 degree terminations, and go to 110.14c, I've got a video that covers conductor terminations, right? But if I'm using NM cable, let's say this is a house. If I'm using NM cable, that is a 60 degree wire, right? I don't care what your motor's rated, I don't care what your breaker's rated, NM cable, you have to have a 60 degree ampacity. So if I'm using NM cable, I'm going to have to pull 10 gauge for that motor, right? Because I need a 25 amp wire, and at the 60 degree column, that would be a 10 gauge wire. If I was doing just THHN, in a conduit, for example, a steel conduit, and I had a 75 amp rated circuit breaker, and the terminals for this motor were rated 75 degrees, then I actually might be able to use the 75 degree column, which would mean I could run 12 gauge. And don't freak out here. I know, like, right up the bat, people are like, 12 gauge isn't 25 amps. Yes, it is. Yes, it is. Look at table 310.16. 12 gauge THHN. Well, okay, you're right. 12 gauge THHN is not 25 amps. It's 30. Okay, it's a 30 amp wire. At the 75 degree column, it's a 25 amp wire. And if our terminals are rated 75 degrees, our terminations, we could go ahead and use the 75 degree column, which would mean we'd run a 12 gauge wire for this particular motor. Let's keep going. 430.22e, other than continuous duty. elevators, drawbridges, garage door openers, wheelchair lifts, varying duty motors, right? For intermittent, short time, periodic, or other varying duty applications, the conductors are sized using the nameplate current rating. Okay, so let's read that again. For other than continuous duty, you use the nameplate current rating, multiplied by the values in table 430.22e. All right, so this is what we call a 60-minute motor. Okay, and you might have a 30-minute motor. This is likely being used in an elevator application. So I have a 60-minute motor. I go to table 430.22e, and it's going to give me a demand. All right, and I'm going to multiply it by that factor, and I'm going to pretend that that's what my motor pulls. So 60-minute rated elevator nameplate of 38.4 amps right there. If I go to table 430.22e, it says for a 60-minute motor in an intermediate duty, you're going to multiply that by 0.9, which gives you 34.56 amps. So I would need an 8-gauge wire at the 60-degree column. I could use a 10-gauge wire at the 75-degree column. Let's keep going. Overcurrent protection. So we know how to size the wire now. Now we got to protect against overcurrent. So basically, overcurrent protective devices protect the motor and protect the conductors from dangerous overcurrent. This is a real tightrope that we have to walk here, because we have to size them to protect the wire and protect the motor and allow the motor to start. So it's a really fine line here, because think about it. If you just size the breaker, let's say I've got a motor that pulls 10 amps, right? Go to the NEC table and it says 10 amps. Could I just put it on a 50 amp breaker and pull 50 amp wire? Well, that would certainly protect the wire. But remember, we have to protect the motor itself as well. So when we talk about overcurrent protection, a lot of people think that overcurrent protection is just to protect the wire. Well, it does protect the wire, but it also has to protect the equipment, in this case, the motor. So it has to be sized small enough to actually protect the motor, but big enough to allow the motor to start. And that's where things can get really tricky, and that's where we might have to do overcurrent protection in a couple of different methods. So a lot of times we'll have to use two different types of protection: ground fault and short circuit protection, and separate overload protection. And we'll talk about what those two mean. Okay, so what is overcurrent protection? Well, overcurrent protection is protection against overcurrent, obviously. Well, what's overcurrent? Okay, well, that's not as obvious. Overcurrent is current that exceeds the rating of equipment or the ampacity of a conductor. So again, we have to protect both. We protect the conductor, we protect the equipment, right? And overcurrent can be from an overload, a ground fault, or a short circuit. And we have to protect against all three of those in order to be protected against overcurrent. If I only protect against overloads, that's not overcurrent protection. That's just overload protection, all right? If I only protect from ground faults and short circuits, that's not overcurrent protection. That's ground fault and short circuit protection. So we have to do all three. So let's talk about what these three mean. Overload, it's pretty simple. Overload is exactly what it sounds like, just too much load, right? Operation of equipment in excess of its rating. Okay, so we're operating the equipment, and the equipment has more current than it's rated for. That's overload. Or operation of a conductor in excess of its ampacity. That also would be an overload. Looking at this wire here, this was from a transformer at a facility where I teach often. They had to replace their transformer because they were overloading their transformer. And when they replaced their transformer, they realized that their brown wires were not brown anymore. They were black. And you can see the discoloration here. I'll show you another picture of the same wire. That would be an overload, right? Short circuits and ground faults are not considered overloads. Overload is simply pulling too much current. You go to your bathroom, you plug in 3 curling irons and a hairdryer, that's an overload. Same installation. You can see down here in the bottom left where that wire started as brown and ended up as black and ended up in a complete total failure where the insulation just overheated and broke. That would be an example of an overload. Or operation of equipment in excess of its rating, right? The donkey here is only rated for so many boxes of whatever that is, right? We put too many boxes on it, it's in an overload condition. So, operation of equipment in excess of its rating, operation of a conductor in excess of its ampacity. Those are overloads. We also have ground faults and short circuits that we have to protect against. A ground fault is an unintentional connection between an ungrounded conductor, a hot conductor, and normally non-current carrying metal parts or the earth itself. All right, so here we had an ungrounded conductor, a phase conductor, that smacked into the metal parts of that faceplate. And as you can see, it welded and arced and sparked and popped and everything else. And believe it or not, the fact that it arced and sparked and left this big old weld mark, that's actually a good thing, because that's indicative of thousands of amps of current, right? If I just took a hot wire and touched it to a metal object that was just sitting on my desk, right, an empty beer can or something, how much current would it pull? Effectively nothing, right? It wouldn't arc and spark, wouldn't do anything. All it would do is energize that can, and the next person to touch it might get killed, right? But here, that thing pulled thousands of amps because it was connected to an effective ground fault current path. So that is a good thing. When it pulls thousands of amps, that means a breaker or a fuse opens and removes the danger. So a ground fault is not like an overload. An overload, I plug in 5 hair dryers and a curling iron, and it's like, slowly starts pulling more than 20 amps, and, within a minute or two, the breaker's gonna pop. With a ground fault, we're talking thousands of amps, and that breaker or fuse had better open in like one cycle, because that is an imminent danger to anybody that touches the equipment. So that would be a ground fault. A short circuit, for all intents and purposes, is kind of the same thing. It's an abnormal connection of relatively low impedance between 2 or more points of different voltage potential. Okay, so 2 phase conductors, right? Phase A and phase B, smack them together, or the hot and the neutral, right? If you take 2 ungrounded conductors or an ungrounded conductor and a ground-dead conductor, neutral conductor, and smack them together, we call it a short circuit. The result is thousands of amps of current, massive amounts of destruction, right? I mean, take a look at this. Drywaller ran the screw right through the wires of this SE cable, and you can see it quite literally blew it apart, right? That doesn't happen when we have 10 amps. That happens when we have 10,000 amps. So when we have short circuits, it's a massive amount of current, it's an immediate danger, and we need the breaker or fuse to open right now, okay? So ground fault protection and short circuit protection are basically treated the same way, because for all intents and purposes, they're the same thing, right? It's the same danger. Just another example here of a short circuit and the after effects, right? When we have a short circuit, the result is thousands or tens of thousands of amps of current, massive amounts of destruction, arc flashes, and all sorts of crazy things happening. So we need to protect our motors from overload and from ground faults and from short circuits. So, sizing the ground fault and the short circuit protection. The ground fault short circuit protection device is sized using Part 4 of Article 430, mainly Section 430.52. All right, let's take a look here. 430.52b actually has kind of an interesting sentence here. It says the ground fault and short circuit protection device must allow the motor to start. Because sometimes people will be like, well, Ryan, I don't want to go through all this crap. I got a 20 amp motor, I'm just going to put a 20 amp breaker on it. Okay, you can try it. And if it works, hey, great, man. Count your money and go home. But what is likely to happen is you're going to turn that motor on and it's not going to pull 20 amps, right? It's going to pull 120 amps for that long. Now, that's not necessarily a danger, but that 20 amp breaker probably is not designed to hold 120 amps for that long. It might trip immediately. So this rule actually says, hey, that's a violation, right? That motor might be protected, but if the motor can't start, that is a violation. The ground fault and short circuit protection device must allow the motor to start. All right, so here I'm showing an example. It's a 460 volt, 30 horsepower motor, which is a 40 amp load, right? Go to table 430.250. And if we're having failure to start problems, we might actually be able to put this on a 150 amp breaker. Okay, now again, pause the video. You can see the language here, and you could follow along in the code and do all the math if you'd like, and it's a good exercise to do. But I don't want to spend a ton of time on it. Just suffice it to say that this motor that pulls 40 amps, we might have to put it on a 150 amp breaker to allow it to start. 430.55, and I'm kind of jumping around here, combined overcurrent protection. This section says a single overcurrent device can be used for both overload protection and ground fault and short circuit protection if it's sized as an overload device. Okay, so let me just kind of throw this out here really quick. Generally speaking, for ground fault and short circuit protection, we size the breaker or fuse at 250% of the NEC table values. We size the overload protection at either 115 or 125% of the nameplate rating. Okay, so there's a big difference between the rating of the overload device and a rating of the ground fault and short circuit device. This section is saying, listen, if you want to size both to the more stringent of the two, the 115%, if you want to do that, that will certainly protect the motor. And if it allows the motor to start, well, then just size it that way, right? Again, if you have a 20 amp motor and you want to put it on a 20 amp breaker, you can, right? But you do have to satisfy this rule that says the motor must be able to start, all right? So remember, these values here are maximums, okay? They're not minimums, they're maximums. So do you have to size the overload protection at 115%? No, you could size it at 100%. Do you have to size the ground fault and short circuit at 250%? No, you could size it at 100%, as long as the motor starts. More realistically, we're going to use table 430.52C1 to size the ground fault and short circuit protection device. It says the branch circuit, ground fault, and short circuit protection device must be sized using table 430.52C1 unless allowed in C1A or C1B, which we're not really going to get into. So here I've got a motor. It is, 115 volts, single horsepower motor, single phase. Don't read the 13.4. That number doesn't mean anything to us, right? Because we size using the NEC table. So 1 horse, 115 volt motor. I'm going to open up my code book, go to 430.248, and I'm going to find that that is an 8 amp load. All right? So 8 amp load. I go to table 430.52C1, and it says if you're using an inverse time circuit breaker, or you're using a non-time delay, or you're using an inverse time fuse, dual element fuse, then you size it at 250%. For a non-time delay fuse, you're going to size it at 300%. So if I'm using a non-time delay fuse for this one, 8 amps, 300% means 24 amps. 24 amps is not a standard overcurrent device rating, and this section of the code allows you to go to the next higher size, which would be 25 amps. All right, so again, could I put this on a 15 amp breaker? Sure, but it might not start. So could I put it on a 20? Sure. Could I put it on a 25? Yes. Could I go higher than that? Maybe. If the motor will not start, okay? You put it on a 25 and every time you turn it on, it melts the fuse. If you do that, then we can go a little bit higher, but generally speaking, 430.52C1, these are the maximums, all right? So, based on the type of motor and the type of overcurrent device, whether you're using a non-time delay fuse or a dual element fuse, or whether you're using an inverse time breaker, which is standard, or if you're using an instantaneous trip breaker. Now, let me just kind of point out here, because look at the numbers here. Look how far out of whack the instantaneous breakers are compared to everything else. It's like 300, 175, 250, 800. Right? 300, 175, 250, 1100. Okay, instantaneous breakers, also known as motor protectors, are only allowed as part of a motor control center, all right, as a listed motor control center. So generally speaking, when we're using breakers, usually we're using inverse time, unless we're using an MCC, in which case we might use a motor protector breaker or an instantaneous trip breaker. All right, so most of my examples, I try to stick with dual element fuses or inverse time breakers, okay? So single phase motors, we know the rule, right? 300, 175, 250. AC polyphase motors, so three-phase motors, right? Other than wound rotor, 300, 175, 250. Squirrel cage, other than his IMB, right? You notice that a lot of these are the same numbers, except for the instantaneous trip, all right? So if you're doing a test, don't lose your mind. You know, there's a decent chance it's going to be 300, 175, 250, depending on the rating of the overcurrent device. Here is what the NEC table looks like here. This is 430.248. This is for single phase motors, right? So let's just do an example and then we'll go backwards. Here I have what do we got here? A 230 volt single phase motor, and it is 5 horse. Okay, so those are the three numbers we need to remember, right? Single phase, 230 volt, 5 horse. Let's go back here. Single phase, 230 volt, 5 horse. That is a 28 amp motor. Let's see if it says anything on here. Does it tell us what the current is here? Not that it matters. I'm just kind of curious. Doesn't say. Oh, no, it does. 22. So this motor says it pulls 22 amps. And in reality, it probably does. But guess what? We're going to size the wire, the disconnect, and the ground fault and short circuit protection device based on the NEC's table values, which was what? 28. All right, so 28 amp motor. If I'm using an inverse time breaker, I'm going to size that at 250% of 28. So what's that going to be? 56 plus 14, whatever it is, 70 amps, right? So 70 amp breaker for my 28 amp load seems a little excessive, but if that freaks you out, then put it on a 30 amp breaker. I don't care, as long as it starts, right? But I can go up to a 70 amp breaker. All right, sizing the overload protection. The overload protection is sized using Part 3 of Article 430, mainly Section 430.32 or 430.33 for other than continuous duty. All right, so here we've got a motor, and I'm circling what's called the service factor, okay? The service factor is basically a percentage of the motor that it's rated to work at. What I mean by that is 1.15 is 115%. So this motor is actually rated to operate at 115% of its nameplate rating for a short duration of time. Okay, so if this was let's just make the math easy. If this was a 10 horsepower motor, this could be subjected to 11.5 horsepower of load and still be okay for a short duration of time. You wouldn't want to run it at 11.5 horse all day. It would wipe itself out. But for a short time, it is rated for that. Now, here's where I'm going to bring this in. Do you remember how I said earlier, the overload protection, the overload is operation of a conductor in excess of its ampacity or operation of equipment in excess of its rating? Well, this motor is rated at 115% of its nameplate. So if the motor is operating at 115% of its nameplate, that's not an overload, right? Because overload is operation in excess of what the motor is rated. So here's what this rule says. For motors rated more than 1 horsepower, a separate overload device is sized at the following percentages of the motor's nameplate rating. 125% for motors with a service factor of 1.15 or more, or a temperature rise of 40 degrees C or less. Okay, so this has a service factor of 1.15, which again is basically a percentage. So if this motor pulls 12.8 amps, and I protected it against overload at 12.8 times 115%, it's certainly protected, right? But 12.8 times 115% isn't yet an overload. Does that make sense? So I'm going to size it at 12.8 times 125% because that would be an overload, and we don't want it to exceed that number. So the service factor of 1.15 or more, or temperature rise of 40 degrees C or less. The temperature rise basically means that the temperature when you start the motor, when it's cold, versus the temperature of its operating condition. Okay, that's the temperature rise, the difference of the cold temperature versus the running temperature. 40 degrees C is 104 degrees F. All right, so I've got this motor, I push start, and over the course of several minutes when the windings start heating up, right, and things start moving, if it's room temperature, right, and it has a temperature rise of 40 degrees C, that means that the windings that were room temperature are now running at room temperature plus 104 degrees F. All right, so that's what the temperature rise means. If it has a low temperature rise, let's say a temperature rise of 30 degrees, well, then that would mean that from the time I start the motor to the time that it's running, it really doesn't get that much hotter. And if we think about an overload, it's heat, right? So if the motor is not heating up, then we don't have an overload situation. But if the motor has a temperature rise of more than 40 degrees, that means that by the time I start it, by the time it's running, that motor is running hot. And if it runs much hotter than it's already running, that's going to be an overload. All right, so don't get your head wrapped around the axle too much here, okay? Service factor 1.15 or more, temperature rise of 40 degrees C or less. Usually you don't really get one without the other, because if your temperature rise is low, well, that means the motor is rated for probably 115, 120% of its nameplate rating, right? So usually you get both. You're not just going to get one or the other. You'll get neither, or you'll get both, all right? If you have neither, then it's sized at 115%. If you have one or the other or both, then you size it at 125%. So for motors rated more than 1 horse, a separate overload device is sized at 115% for all other motors. All right, so here I've got this motor, service factor of 1.0, which means the nameplate rating is the rating. If it's pulling more amps than the nameplate rating, it's in an overload, all right? Ambient temperature says 40 degrees C. That's the ambient temperature rating, all right? That is not the temperature rise. So when you see 40 degrees C ambient, that's a very, very common number to see in motors. That just means that it's designed to be used in a 40 degree ambient temperature, which, like I said, is 104 degrees F, all right? So if you're more than 1 horse, separate overload device is sized at 115% of all motors unless it has a high service factor or a low temperature rise, or both. This part's really important here. 430.32A2, integral thermal or electronic protection. A motor that has built-in thermal or electronic overload protection integral to it does not require separate overload protection. All right, I'm seeing these beautiful words here that says thermally protected on this motor. Cool, what does that mean? Well, if you're familiar with a garbage disposal, you ever done the dishes and you dropped your fork and then you turn the disposer on, you didn't realize that you dropped the fork down the sink, and you turn the disposer on and there's a fork down there and it shakes, rattles, and rolls, right? It makes all sorts of racket. If it lands just perfect, that fork gets down there and it blocks the blades, which puts it into what? Locked rotor condition, right? That rotor is locked in place. We know what locked rotor condition looks like. It's like, 6 times the running load current. Well, that is certainly an overload condition. And if it lands just right and it locks that rotor, for a disposer, those have integral thermal overload protection. That motor will stop, okay? Without you having to hit the switch, that motor will shut itself off. And in order to get it started again, you have to do what? Shut the switch off first, right? You have to reach under and you have to push the button on the bottom of the disposer that resets what? It resets the overload protection. All right, so that disposer has built-in overload protection. It will not allow itself to just run itself into oblivion. Because think if it didn't have overload protection. You put that knife down there and the motor's spinning and it locks up and more and more and more current is going to flow, right? That motor will probably smoke before the breaker trips. That's an overload, right? So for small motors, usually overload protection is built into the motor, okay? So here, this one is thermally protected. So how would I wire this particular motor? 230 volt, 5 horsepower, 430.248 said that's a 28 amp load. Remember that? So I would need a 28 amp wire, and I could put it on a 70 amp breaker. Now, here's where people lose their mind. Like, oh my God, Ryan, you're going to burn down every house in America. No, I'm not. Listen, we've used motors since like 1890. We got to figure it out, okay? This is not going to kill anybody. If you have a 28 amp wire on a 70 amp breaker and it's for regular loads, like a water heater or something, yeah, you're going to burn the building down. But for a motor, all we're doing with that 70 amp breaker is what? It's not overcurrent protection. It's ground fault and short circuit protection. Ground fault and short circuit protection at the breaker plus overload protection at the motor equals overcurrent protection. All right? So I only have ground fault and short circuit protection upstream, overload downstream, and I size the wire for the load of the motor. Not 115%, right? Not 250%. You size it at 125% of the load, and that's how you size the motor. So you need a 28 amp wire times 125% would be what? 35 amps. So 8 gauge wire, 70 amp breaker. That's what you would do. Now, what's keeping that 8 gauge wire from melting? Well, if we have a ground fault or a short circuit, right? So here's the cord of the compressor motor, right? Somebody takes their dikes and cuts the cord while the motor's spinning. That's a short circuit, right? That's taking the two hots, bam, and banging them together. That's a short circuit. We're going to get thousands of amps of current. Think about what that's going to do to your dikes, right? Because it's thousands of amps. Is that 70 amp breaker going to trip? Absolutely. It's going to trip immediately. That's ground fault and short circuit protection. Covered. What if this motor starts to act weird though, and it starts to slowly pull more current than it's rated for? Well, it's thermally protected. It will shut itself off. So how am I going to melt the insulation off that 8 gauge wire if the motor shuts it off as soon as it starts pulling more than, 22, 25 amps, right? Internally, that overload protection for that motor is probably set at about 24 amps. If it starts pulling more than 24 amps, it will shut itself off. The wire was rated 35 amps? So how are you going to melt the insulation off the wire? You're not. You have overload protection. You have ground fault and short circuit protection. They're just at 2 different locations, all right? Now, if you have a bigger motor, it's not going to be inherently protected, and you're going to have to provide overload protection separately, right? And you might do that in the form of a combination motor starter, which is like a disconnect and built-in thermal overload protection, right? Heaters, basically, or electronic relays, okay? That's going to be your overload protection. This is a motor that says it's electronically protected. Same thing. Instead of actually having a thermal element inside of it, it's got an electronic element that senses how much heat is going through the motor, and it will shut itself off, if it's operating in an overload condition. All right, so that is the overload for that motor. So same concept here. If this was a 20 amp motor, you would size the wire at 20 amps times 125%. You would size the breaker or fuse at 20 amps times 250%. So a 50 amp breaker on 25 amp wire would be fine for this particular motor. Right, now again, can't do that with receptacle circuits and lighting circuits and appliances, but for motors are different. Let's do one more example here. 430.33, intermittent or similar duty. Remember I said all motors are continuous duty unless they have a definite starting and stopping point. Well, if they do, right, for motors that are not used in a continuous duty application, the branch circuit, short circuit, and ground fault protection device sized in accordance with 430.52 can be used for overload protection. You're not nearly as likely to get an overload on a motor. Like, again, think of your garage door, right? Your garage door opener goes from here to here. That's it. In that little tiny span, how likely are you really going to have an overload? You're probably not, right? So for an intermittent or similar duty motor, we can just use the ground fault and short circuit protection as the overload protection, all right? You don't have to have a separate overload. You don't have to have built-in overload. We can let the ground fault and short circuit protection protect the wires and protect the motor for all three overcurrent conditions. All right, let's wrap this up. If you want to be good at golf, play golf. If you want to be good at the NEC, you need to use the NEC. Don't just watch my videos. Don't just read textbooks. Use the NEC. Apply it, okay? Find examples in the real world. Take pictures of motor nameplates, right? And I know it's like, oh, this guy wants me to take pictures of motor nameplates. No, I want you to be good at your job. I want you to pass your test, all right? And if you want to be good at your job, if you want to pass your test, if you want to be good, you have to do. You can't just read, you can't just watch, right? If you want to be a good tennis player, you have to play tennis. You can't just watch Wimbledon. You actually have to get a racket and you have to play. If you want to be good at the NEC, find some motors, do the process, figure it out. Okay, got a single phase motor, it's 5 horsepower, 230 volt, flip back to 430.248, right? And it says, okay, that's a 28 amp motor. 28 times 125%, that's 35 amps. Find a 35 amp wire in table 310.16. There's your wire. Do your overload protection. Is the motor inherently protected? If it is, great. If not, probably going to have to do separate overload protection, right? Figure out your ground fault and short circuit protection device. 5 horsepower motor, single phase, that was 28 amps times, 250%, it's going to be 70 amps. So work the process. Do as many examples as you can. Article 430 is super intimidating, and it's very unusual. We treat motors so differently than all other types of circuits. But once you understand why we do it, it makes sense. And once you do more and more examples, you'll be a lot better at it. All right. I think that's it for today. I hope you enjoyed the video, and I hope that you're working safely out there, and I hope that you're having a great day, and I hope that I'll see you again soon. Thanks, everybody. Be sure to like, follow, subscribe, and ring the bell.